Hi, Assalamualaikum and very welcome for those watching this video, especially for Miss Sam, our physics lecturer. So in this video, me and my group members are going to present our laboratory experiment of experiment 5, which is Hooke's law. Let's start with introduction first. So generally, Hooke's law can be explored by observing how much a spring stretches when a known force is applied. And the fact thing is, this force is easy to calculate by hanging a weight at the end of the spring and using the formula which is F equal to ma, where F is force, m is mass, and a is acceleration. This is also means that the force depends on the weight of the object and the gravitational pull that acting on it. It's simple, isn't it? So let's move on to objective.
So the objective of this experiment is to verify the accuracy of Hooke's law. Next, from the Hooke's law, the theory stated that the motion of a body that oscillates back and forth is defined as simple harmonics motion if there exists a restoring force that is opposite and directly proportional to the distance x that the body is displaced from its equilibrium position. So the relationship between the restoring force and the displacement x can be written as force F equals to negative k times x, which the k is a constant of proportionality. So the minus sign before the k indicates that the force is oppositely directed to the displacement and is always towards the equilibrium position. To do this experiment, you need helical steel spring with supporting stand and scale, and you need digital weight balance to measure the weight of the slotted weights, and you also need a set of slotted weights with the hanger. Now, let's do the experiment. First, you need to measure and record mass of the hanger, and then you need to calculate the weight of the hanger and record it as W in the table. And then adjust the scale so that the pointer on the hanger is near the upper end of the scale when the hanger is unloaded, and record its position as x0. Load the hanger by 10 gram mass and then record the scale reading as x1, and then keep increasing the load by suitable increment. They need to be equal to obtain 8 data points before the lower end of the scale is reached. Record all data, W and X1. And then reverse the process by unloading the same loads as in number 3. And again, record new scale reading X1 for each load. Calculate extension of the spring, uncertainty X, and then finally determine the extension force acted on the spring F for each total loads.
So this is our data. As you can see, this table represents experimental data where the extension of a spring is measured under different loads. The key variables are as follows: loaded mass, the mass added to the system in increments starting from 0.01 kilogram and increasing by 0.01 kilogram up to 0.08 kilogram. The total mass of loaded mass and hanger, so presents the combined mass of the weight and the hanger. So the hanger seems to have a constant mass of 0.01 kilogram. So and then we go to weight of loaded mass and hanger. This is the total weight, they're calculated by multiplying the total mass by gravity, which is 9 meter per second. So for each step in mass, the corresponding weight increases proportionally. Next, the extension and force. This shows the force applied to the spring, which is the same as the weight, since force equal to weight in this context, right? So yeah, and then the scale reading with load. This shows the measured displacement of the spring under the applied force for 2 trials. And last, extension of the spring. This is the difference in the scale readings with load showing the extension of the spring at each load level. So let's move on to analysis. So this graph illustrates how the force is applied to a spring changes as the spring is stretched. When you pull a spring, the extension, which is like along the horizontal axis, is increased. The required force is also steadily rises as shown on the vertical axis. For example, like at the extension of 0.1 meters, the force is about 2 newtons. All I can say is this steady increase shows that the spring behaves predictably. I mean, like, it's following the Hooke's law, which is essentially means that the force is directly proportional to the amount of stretching, which is extension. So as you can see, this is our analysis. So the first question is wanted to calculate the gradient of the graph. So here we use the first force is 0.20 newtons, and then the delta x1, which is represent the extension of the spring, we use 0.1 meter, and then f2 we use 0.90 newtons, and in delta x2 we use 0.x meter. So the formula gradient is k equal to f2 minus f1 divided by delta x2 minus delta x1, which is the extension of the spring. So simplify, we got 1.0 nano per meter. And then it says, what value does the gradient represent? So generally, the gradient is represent the spring constant, which is k. And then question number 2, how much work done in stretching the spring through 0.20 meter? Find this from the graph. So once the extension of the spring is 0.20 meter, right? So we use the formula is W equal to 1 over 2k delta x square, which k is the gradient that we got from question 1, and then the delta x square is from the question that given. So yeah, just key in the value, and then we get the answer is 0.02 joule. Question number 3, it says how much energy is stored in the spring when it is extended to 0.20 meters. It's just same from number 2, but we just change the work from energy. Use the same formula, simplify, and then we got the answer is 0.02 joule. So let's move on to question number 4. Describe any errors that may have occurred during this experiment. So as you can see, here's the measurement errors. It's possible that the measurement of the extension or the force weren't perfectly accurate. And then number 2, spring wear and tear. If the spring had been stretched too far before or during the experiment, it might not follow the ideal rules of a perfect spring anymore. And third, external condition. If the environment like room temperature, it'll affect the spring's material. It will change the way the spring behaves. And last, human mistakes. Like people could have read the numbers on the measuring tools incorrectly or placed errors which would affect the data. And then let's move on to question number 5. What can you describe from your result about the relationship between the extension of a spring and the force causing extension? As you can see, the results show that the force needed to stretch the spring increases in a linear way as the spring stretches. This confirms Hooke's law, which says that the force required to stretch a spring is directly proportional to how far you stretch it unless the spring is stretched too much, which would break the pattern. That's all for analysis. Let's move on to discussion. So here the discussion. So from the experiment, we noticed that as the spring length is in meters, it all increases. The spring's elongation also increases. This happens because weight which we adjust during the experiment directly affects the spring stretch. So in this case, the weight acts as the force applied to the spring. The weight of each mass can be calculated by using the formula which is W equal to mg, where W is weight, m is mass, and g is gravity. So based on our results, we observed that increasing the mass causes the spring stretch more. This shows that the mass of an object is directly proportional to the spring's elongation. In this experiment, the mass is the variable we changed, while spring's length is what we measured. Initially, without any mass, the spring's length was 0.065 meter. When we added a scale pen weighing like 0.005 kilogram, the spring stretched to 0.075 meter, increasing its length of 0.010 meter. We then added a 0.025 kilogram mass, and then the spring stretched further to 0.127 meter. what we call this, it's increasing by another 0.010 meter. Yeah. And then we repeated the process with masses of 0.050 kilogram, 0.075 kilogram, and 0.100 kilogram, also 0.125 kilogram, and 0.150 kilogram. Each time, we found that adding more mass caused the springs to stretch more. Yeah, from this, we can say that as the force on the spring increased, so did its elongation. Yeah, so our findings align with Hooke's law, which states that the force needed to stretch a spring is directly proportional to how far it stretches. This relationship can be expressed using the formula like F equal to kx. And then, we know that the force is what's needed to stretch a spring. Also, the constant is the spring stiffness and how far the spring stretches. So for this experiment, we are looking at the stretch that caused by the force. Like on the graph, we can see that the force is on the y-axis and the stretch is on the x-axis. Using this, we can calculate the spring stiffness using the formula, which is K equal to F divided by delta x, where K is the spring constant, F is force, and delta x is represent the what we call this, the extension of spring. Yeah, that's all for our discussion. Let's move on to the last part, which is conclusion.
In conclusion, based on the experiment, we can conclude that the elongation of the spring depends on the stiffness of the spring. We can determine the stiffness of the spring is the spring constant. The bigger the spring constant, the shorter the elongation of the spring. The experiment is related to the theories. That's all from us, and thank you for watching.